to implore you, start studying as soon as you can. We've shot for the moon in this course. We've gone for a lot of hard principles to really understand them well, and I'm going to see who got it. So start studying soon, and as many sittings as you can break up your studying. The research says that the things you remember from your studying is when you first sit down and study, and when you just before you take a break. So what does that mean? Do lots of little time studying. Don't try to study 4 or 5 hours at a time. Study for an hour at a time. Okay? And as many hours as you can. Make study groups. That's really great if you're in conversation and working together. And then bring your group to my office on Monday, okay, or Tuesday, and we'll all work together. Okay. Other questions? All right. So I want to do just a few more of these. And this is actually from the homework. So we're going to do some harder antiderivatives, and we're going to talk more about area today. So this is the actual homework. We're going to find some examples from the actual homework assignment that's due Monday. So let's see, maybe 7. Lucky 7. Lucky 7. Beautiful. Love it. Okay, so here, let's talk about, so these harder antiderivatives are, these particular ones we want to talk about are undoing the chain rule. So let's review the chain rule. So undoing the chain rule means you really understand the chain rule itself. So what kind of function is the chain rule about in terms of finding the derivative? What kind of function? F of? A composite. So if we want to find the rate of change of f of g of x, what does that look like? Yeah, we look at the big picture, right? And we take the rate of change and the overall structure. And what about the inside?
Multiply by the rate of change the inside.
It's not multiply.
Oh, it's just the rate of the change with respect to
that's the same.
inside.
Then
G prime or G in here?
G.
Leave the inside as it is.
Then what?
And then the chain rule says we need that scaled up, right? We need to scale up by the rate of the inside. So if we're undoing the chain rule, then we have this. So we have to recognize what we have here. So for the most part, it'll be a product of two things. And we're trying to recover the original function if we're doing an antiderivative. So therefore, if we see this product and we want to recover the original function, which of these two are we going to focus on? Are we going to focus on here, number 1? Or are we going to focus on number 2 if we're trying to recover this? What clearly should we focus on to try to recover the original function? Number 1 or number 2? Yeah, number 1, right? Number 1, because look at our result. Our result is just like this. There's only one thing we have to do, and what is that? Yeah, we're going to do the antiderivative of the overall structure of this. And what about what's inside? It's going to stay the same. You see? See, so when we go backwards, this automatically collapses back inside. So our focus, when we're trying to do this, undo the chain rule, our focus is going to be on the composite part. And the bulk of it is to find the antiderivative in the overall structure, f. So we have f prime, so we want to recover f, and g stays the same. Does it make sense? Now, and then there's a little mess to clean up. We've seen this in some examples so far. We get constants that we need to multiply, coefficients that we have to clean up. But the focus is here, and we're going to do the antiderivative of f. That's the bulk of it, okay? So here's one. We'll write it bigger. So which of these two is our f prime g? Is it the first or the second? Which of these two is our f prime g? The first or the second?
Second.
He says the second. Do you agree with that? Yes. Right. And what is f? Or what is f prime? Or what is the overall structure of this? Is it exponential? Is it sine? Is it ln? Is it a power? What is it?
Power.
Yeah, it's something to the eighth. So our f prime is something to the eighth, and we want to recover f. So we're going to make a first attempt at this. And our first attempt is going to be what? Our first attempt. So we're going to leave the inside as it is, going backwards, and we're going to take the antiderivative in the big picture, or in the overall structure. So tell me. Yeah, Kevin.
The quantity of r cubed plus b to the ninth over 9.
To the ninth?
Yeah.
And you want
Over 9.
1/9 of that. And then we have, this is an improper integral, so really we have all antiderivatives, right? All antiderivatives, meaning we got plus c. What do you think about his first attempt? So this is almost the answer, right? If we follow the chain rule here, we've almost got it, because we went backwards and we took the antiderivative in the big picture. That's just a first attempt. So how do we check it?
Is b a constant?
It's 6.
Oh.
But if it were b, yes, it would be a constant. Okay, so how do we check it? Or is that a different question?
No, I was just going to add to.
You're gonna well, so if you can see the answer, so some of you right now can see what the true answer is, and that's great. But this is and if you can't, then what do? We make a good educated guess, and then what do? Check. How do we check it? Take the derivative. Ross, do it. You said that, right?
Yes.
Okay.
So you take off 1 9 times 1 8 to the 9, multiplied by 9.
9 times 1/9 is 1.
And then take the whole thing to the 8.
Keep the inside the same. This is now, we're doing the mastery test, right? To the 8th.
And then you take the derivative of the inside, which is r squared. Or no, 3r squared.
3r squared. Any more?
No.
That's it. So now we compare. We take our checked version of our first attempt, and we compare it to what we started with. If they match, we're done. Our first attempt was right. But if they don't match, then we just got to clean. We got a little mess to clean up. Do they match? No. So, second attempt. How now that we've seen how our derivative compares to what we started with, how would you adjust the first attempt?
Instead of r squared, would it be 1/3 r cubed? 1/3 r cubed.
You want
in
one?
Parentheses.
No, because then we'd have, if we take the derivative, we'll have 1/3 r cubed in the parentheses. That doesn't work.
Yeah.
You see? Because you're leaving the inside the same.
Right.
So what do we need? How is this different than this? Yeah, it's 3 times 2 great, right? The only difference is right here. This is 3 times this. So therefore, our first attempt was 3 times 2 great. So second attempt would be? 77. Right, sorry. Right, so we need 1/3. Another, right, sorry. And then if we want, we can check again. Or we can be confident we're not going to check. But if we checked, we'd have it. Because that 1/3 and that 3 would be 1, and we'd have exactly what we started with if we took the derivative of this. So does this process make sense? All right, so let's we'll do one more harder one, and then we'll go on to one last topic. Anybody have a question on this one? So we've already been kind of doing this, right? We've already have done one similar to this, and now we're just formalizing that. What are we doing? We're undoing the chain rule. So it's really about just understanding what the chain rule is. So let's find one that's a ratio here. There we go. So the result of a chain rule, what kind of thing is it in general? The result of chain rule? Is it a quotient like this? No, what is it? Product, right? It's the product of f prime g and g prime. But we got a quotient. It doesn't phase us because we can rewrite this as a product, right? We can rewrite it as e to the 5x times,
E 5x plus 8 to the negative 1.
yeah, or 1 over. Okay, where's our focus? Curtain number 1 or curtain number 2? We want the composite function. Okay, so now we look at the overall structure of this, something to the negative 1 or 1 over. And we want to do the antiderivative of something to the negative 1 or 1 over. What is that? What is that the derivative of? Natural log. Okay? And remember, we want absolute values. Okay? What's that? We don't have time, so office hours. Office hours, sorry. Because very quickly, the domain of natural log is only values greater than 0, but this function allows for all real numbers. So that's just a very quick explanation. Okay, so that's our first attempt. How do we check it? Take the derivative. Derivative is 1 over. And what's the derivative of the argument? That's 5. Okay, so this is our check. Do we need to adjust the first attempt? By what? Our thing is what? 5 times 2 great. Here's the problem that we don't have here. So this is identical, but then it's times 5. So we need 1/5 of our first attempt. Now, for this particular one, this will always be positive, an exponential function plus 8. So actually, in this case, those absolute values are optional, but it doesn't hurt to write them. Questions on undoing the chain rule? Yeah.
Would it be wrong if you just divided everything by 5 instead of doing like 1/5 of natural log? So like
And that's the same thing, right? Multiplying by 1/5 and dividing by 5 is the same thing.
That first one, you took 1/3 of the 1/9. Do we need to simplify that further? Or is that okay?
Yeah, you should. Well, yeah, it's the same value, but yeah, 1/27.
You just were showing us.
I was showing you, right? Yeah, but 1/27 would be more efficient. Okay, so when you get to Calc 2, maybe one of the first things you'll do in the course is you'll learn something called, if you can remember this, U substitution. U sub, okay? If you become good at what I'm teaching you here, you don't need that for most of the time. And this will feel, so for some who have learned this, it feels like a security blanket. But for those who get good at this will be like the worst tasting thing ever, okay? Because it's just all these things that all these steps that you're memorizing, and it doesn't really seem to make sense. So I encourage you to, there's 14 problems here, you'll practice. So when you get to use substitution in Calc 2, most of those problems you can do what I've taught you here, which is the undoing the chain rule technique, okay? Which is, in my opinion, better because it's really about understanding the chain rule, okay? Where use substitution is very, very methodical and it's just, yeah. And if you forget what to do, you got it wrong, right? It's a procedure that you memorize, and if you forget what to do, you can't do it, all right? But if you know the chain rule, then you can undo it, okay? Questions on that? Yeah.
How would that be different
If you had what?
specified region that you were finding?
Oh, well, so this is, yeah, so good point. So there's some of the questions that have, say from 2 to 10, right? So now that you've got the antiderivative, you're going to evaluate that from 2 to 10, just like we did. So it's not different. It's just that you'll have the last step of plugging in 2, plugging in 10, and subtracting. Yep. So there's no difference except for you have actually find that net accumulation in the last step. Yeah.
If we plug that in, how does it C, like the plus C, do we just add the plus C?
So this will work for any antiderivative because when you plug 10 in, you'll have C, and when you plug 2 in, it'll be minus C, and it'll go away.
Oh, okay.
So no matter what antiderivative we pick, that will always cancel out in the subtraction. Yeah. Other questions? Okay, we have one last important topic. So I showed you this slide before, and this was looking at, we're accumulating starting at, our reset is A, so this is 1, A equals 1. So this is basically showing us the accumulation function from 1 to x of RT dt. So there's our, at 1 we get the accumulation is 0. Okay, and so then we have some x value that we're plugging into our function, and that function gives us this amount of accumulation, right? And how does it find that value right there as an estimate using this step function? Do you remember that? So it's going to what? It's going to calculate that by little bits of accumulation one at a time. And how does it find each bit of accumulation?
K delta x.
Right, R1 times the first delta x, R2 times its delta x, etc. And so we worked hard on this in the first half of the course, that this thing represents the sum of many bits of accumulation. Each one of these is a bit of accumulation. German S, we're summing them all up, starting from 1 up to the current value of x. Okay, and so then we said, when we talked about this midway through the semester, there's an alternate understanding that R1x can be seen as this area because the height of that rectangle is R1, or that rate can be thought of as that height, and then the width of this rectangle is delta x. So that equals the area of a rectangle, say call it A1. And similarly, R2 and R3, and so we said that that the fact that this is remotely related to areas is an artifact of graphing in rectangular coordinates. The only reason this works is because of how we set up our axes, rectangular. Okay, so it ends up that these little bits of accumulation could be forced to be areas of rectangles. Remember talking about that? Okay. So, and then this is also in Calc 2, there will be an emphasis on area. That's why we're going to have this conversation today. But so when you think about each area of those rectangles, so we know what the deeper meaning is. Each one of those quantities, is what? A little bit of accumulation. That's where that came from. And then it's kind of like, oh, look at this. You could also see that as an area. But what it really is a little bit of accumulation. And we're adding all those together. Okay, so this idea of area of rectangles, not deep, okay? Not a profound thing. So, if we make those delta x's smaller, then those rectangles get skinnier, and what's happening? It's actually approaching some total area, right? And what total area is that? So it's the total area as x gets very, very small. Adding up those very, very, very thin rectangles then generates the area bounded by the curve on the x-axis. So we could see this as this area, this blue shaded area that I just graphed, is the integral from 1 to x of RT dt, for this being x right here. Does it make sense? Before we do an example, do you follow that? So equivalently, so we looked at the sum of little bits of accumulation. We let x get very small, and we got the true accumulation. So in terms of area, same thing. We're summing up rectangles, areas of rectangles, and we let x get very small, and that basically then that integral then would calculate this area between the curve and the x-axis. Okay, but just remember that's more superficial than accumulation. Okay, so here's this function, g of x equals 3 minus x plus 2 times x minus 3. And we're interested in what's happening from negative 0.5 to 4. Okay, and there's this thing called the net area. So before we actually dive into this, let's ask the question. If we want to find the net area bounded by this graph and the x-axis, then for us, how can we make sense of g of x? Does g of x, does that relate as an accumulation function or as a rate function to all that we talked about? So would g of x relate or be like an accumulation function or like a rate function?
I mean, accumulation.
It'd be like an accumulation. What do you think? Everyone agree with that?
I think so.
Let's go back to this picture here, right? So here's our curve for which the integral does what? The integral finds the integral from 1 to x, rt dt, finds the area between what? A rate or an accumulation? A rate, right? So this is the rate function. So if we want to, in this area problem, if we want to relate it to what we've done, then it's kind of like we're looking at this g function as a rate function, right? As a rate function. Okay, so we want to find the net area bounded by the graph of g from negative 0.5 to 4. So let's, instead of answering that question, let's write the integral and ask what the integral calculates and then relate it to our question. So let's write this integral here of from negative 0.5 to 4 of g of x dx. And let's ask, if this were a rate function, what is the story of the accumulation from negative 0.5 to 4? So how does our quantity accumulate? How can you describe how our quantity accumulates from negative 0.5 to 4? What would happen? Can you imagine the accumulation? As it would transpire from negative 0.5 to 4. What would be happening at first?
The graph that you're showing, that's the rate of change graph, right?
Okay, so if it's area, then it relates to rate. That's right.
Yeah, okay, cool.
So the accumulation, at first, what's happening to the accumulation? Increasing, right? We have a positive rate. And then what happens here? Now it's going to go down until here, and then the accumulation is going to start increasing again. Okay? So what does this calculate in terms of accumulation? The whole thing. So for the red parts, in this part, there's going to be a positive contribution to accumulation, and over here too. But then what about when we're accumulating between those two? There's going to be a negative contribution to the accumulation. All right, so this is finding the net change. Right? Wherever the rate is negative, it's going to reduce the accumulation. It's going to decrease it. So if we call these areas, so areas are always positive, okay? So let's call this A1 and this A2. That's the positive area, and this is the positive area. Then in terms of these areas as positive values, what does that integral calculate? does it calculate A1 plus A2 plus A3? If those are all positive areas. Is that what it calculates? He says yes. What do you think? Ross says no. Jonathan, what do you think?
You said if A2 is positive?
Yeah, areas are always a positive value. But now we're asking, what does this calculate, right? So we're asking, what does our integral calculate relative to those positive areas?
Those are just a collection of all the accumulation bits,
Right.
So then, yeah, I want to say, yeah. That
But what happens to the accumulation from here to here?
goes down.
Does it go up? No, it goes down because these rates are negative. So the contribution of this part of the net accumulation is negative. So do we want to add A2?
Minus X.
Yeah, so we're going to take that positive area and minus it.
I was thinking in terms of setting up terms, not, I guess that's what I was thinking.
Yeah, so
Terms.
areas are always, when you declare an area, it's always a positive amount of space, right? But we know that whenever the rate function is negative, there will be a decrease in our accumulation. So we've got to take away, or take the opposite of A2 in order for this to equal our net change.
Wait, so is that to prevent a negative value of area?
Nope, areas are always positive. We're trying to write this integral as in terms of these positive areas. And so we have to understand what the integral does to do that.
Are you subtracting?
Hold on a sec. Hold on a sec. Did I answer your question?
Yeah, but I don't understand why you wouldn't just do an absolute value.
Of what?
A2 and A1 and A3 separately.
They're already positive. They are positive values. Areas are positive no matter where they are, because it's how much space you have. Okay? So the question is, how do we represent that in terms of those areas? So what does this do? Positive accumulation is increasing, accumulation is increasing, but now accumulation is decreasing. It's reducing, and then it's going back up again. All right? And so the amount of accumulation through here is a negative value, but if this is positive, then in order to represent this integral, we'll have to take the opposite of it. Does that help?
Yeah.
Kevin, were you talking?
Well, what I said was, it's gonna sound dumb, but are we just adding, are we subtracting a positive value? So-
Yes, exactly.
Yeah.
That's a positive value of area, but we need to subtract it because as accumulation, our accumulation decreases, right, through that.
Well, my also question is, does the fundamental theorem calculate this, or we have to do this ourselves? Like, does it like the?
If you were just to evaluate this with a fundamental theorem, it would be the same value as adding these and subtracting that area.
Okay, so it does account for the
Right, because it's about accumulation, right?
Yeah.
What does this do? It accumulates from negative 0.5 to 4.
Okay.
And what happens in this space? What happens to the accumulation? It goes down.
Oh, okay.
That's built into this.
Yeah, that would have to.
No, that's built into the integral because the integral is accumulation. When the rate is negative, accumulation goes down. So if you want to write this in areas, you've got to finagle your areas that are all positive in order to represent this thing that automatically
for us.
makes the accumulation go up when the rate is positive, makes the accumulation go down when the rate is negative. Okay, good questions, good discussion. Does it make sense?
Yeah.
Okay.
I thought you were getting to we'd have to do the integral from where area 1 begins and ends, and then minus the integral from where area 2 begins and ends, and then plus the integral.
So I'm asking the opposite question. I'm saying, what, given this integral of the whole thing, how would we write it as areas?
Okay.
You see? Or how would, in terms of those areas? Okay. So your turn. Find the net area bounded by this graph. So can you write an expression? Can you write an expression that will find the net area? In other words, what will it do? It will. I don't want to show the answer yet. Okay, so this is A1. and A2 and A3. So by net area, what do we mean? Which ones are positive and which are negative? A1 is, we're going to take the opposite of A1 if we want to get net area. And we're going to take A2 as it is, but we're going to subtract A3. And that's this idea of net area. So we want to write an expression that will calculate that. So can you write an expression that will calculate the opposite of A1 plus A2 minus A3? Most efficient expression you can write.
I just have a question.
Sure.
With the reason why we don't put the absolute values is just because it's redundant, correct? Like putting like the A1, like the absolute value of A1.
Yeah, areas are always positive values.
Just like this.
Areas, just like, yeah, right. So area is always the amount of space that a region takes up. So it's always positive. So how could we calculate this thing net area where we subtract the ones below and add the one above? What could we do? So what expression will calculate that? Yeah?
Would it be the integral from -0.5 to 4 of f of x, d of x?
The same thing as last time. The same thing as last time. Okay? Shoot. That's right where I wrote it. Okay? Yeah, it's the exact same thing. This expression, integrating all the way from -0.5 to 4, will automatically take the opposite of that area. Why? Because accumulation is decreasing. It will add all that area because accumulation is increasing, and will automatically subtract that area because accumulation is decreasing. Does it make sense? Okay, so now, what about this? Find the total area. Okay, go. So see if you can write an integral expression that will find the total area. Now this is the more significant kind of question, okay? So go. Can you find the total area with an integral expression? Oh, so you might need some. Okay, we'll call that x value x1 and that one over there x2, okay? That's a hint. You're going to need those, right? You're going to need those. Write an integral expression that will find the total area. Just use x1 and x2. You don't have to guess what that number is. Just use that.
Yeah.
Okay, no absolute value. Try to not do this without absolute value. Try to do this without absolute value. Okay, that's kind of the point. Because even if you did use absolute value, you'd still, in order to evaluate it, you'd still have to do what I want you to do. Okay, so let me ask this question: does our integral from -0.5 to 4 do it? So who thinks, so you're saying, so what do they call this? G? This back to G again? Will it calculate the total area? No, right? Because what happens in this one? When you do this, what happens to that area? It gets subtracted because the rate is negative, accumulation's decreasing in that part of the interval. Doesn't work. So how are we going to get total area? Melody?
I had 3 separate integrals.
3 separate integrals, okay?
-0.5 on the bottom of the German S, and then the top of the German S was x1,
Okay,
and then g of x,
right?
plus
Integral from,
x1 to x2,
Uh-huh.
but that's minus from the first one.
So you're going to add that second integral or subtract it?
It's subtracted.
Subtract the second integral.
And then the next one is from x2 to x, or to 4.
Yeah. Is this what you did?
Yeah.
So in order to get that area, we're going to need to take the opposite of the integral, because we know that integral in that from x1 to x2 will be a negative amount of accumulation. So to get that area, we take the opposite of it, and then put them all together. Okay. So does this relationship between accumulation and area make sense? And if you truly want it, there's some homework problems with this. If you truly want to find total area, you've got to break up your integrals so that you take the opposite of wherever that rate function is negative, wherever that area is carving out below the x-axis. So you could do this. So in terms of absolute value, you could do the integral of the whole thing of the absolute value of g. But solving that still requires this. So you could do negative 0.5 to 4 of the absolute value of g. And that equals this whole expression. But solving that still requires that you break it up, because you got 3 different functions. Okay, so the 3 sets are posted. Just work on them, and I'll let you know how the credit will go. Look for email. Look on Blackboard announcements. Come see me and ask questions Monday and Tuesday. Okay? Oh. Shoot. Okay, so if you can stick around, there's a bunch of work I forgot to hand back. If you want to stick around and get your work, I'll have that for you.
Yes.
Yeah.